Let's start with the term dielectrics here. So this is the class 12 topic that we have picked it up, and we will be going into the details of it in a much greater way than what we have done in the secondary classes. So we have various learning objectives over here. So first, what we will do is we will start with the term itself. We'll use the etymological approach to understand what does this term means, or at least it will give you an idea of what concept has been made by keeping in mind various properties of these substances that are around us. So if I break it down, I have got dye and then I have got electrics here. So what does this mean? So dye is coming from the term dia, right? And this electrics is basically associated with the term of electrons, which you have pretty much studied up till now. So dia basically means passing through. What we will understand later what is passing through what medium it is passing through, what is the significance of this entire definition that we'll be creating. But first, I'll just leave some hints for you to understand how do we understand the concepts that are given out there. At the end, all of them are made by the humans. So they are created based on some plausible logics, right? So let us understand the dielectrics. So if we go by the textbook definition of dielectrics, you will find that it is basically referred to the substances which are non-conducting. So you have to understand the term non-conducting. But we also have insulators, which you have studied in your previous classes. There were two classifications of the materials, insulators and conductors. So why don't we call dielectrics as insulators? Why have we given a separate term for such substances? Maybe because they follow some new properties, some unique properties, some unique applications, and we will find them out in this video. So our one of the learning objective comes from here, that why is it not being called as insulator? What is the difference between the two? So we'll find that out. Now next we will understand. So if it is not being called as insulator, so basically it is following certain unique properties, right, which are not available in the case of insulators. So from these unique properties, we have various learning objectives that we are going to study. We have various terms like polarization, very important concept, which is also used to define and make a classification of insulators and dielectrics, which I will be telling you. Electric field, because this is going to come out time and again. So we'll understand in detail what electric field is. Then we have a dielectric constant. Why do we have this new term here, dielectric constant? What is the significance of it? Then we also have the electric dipole moment. Now, this is again a new term. From this one topic, we have various subtopics that are associated with it, and they're already giving you the features, giving you the hints of the features of this dielectric topic. Next, we have dielectric breakdown. So these are our keywords that we are going to understand, and also our learning objectives in this video. And all I'm taking is on the basis of the CBSE class 12 physics. So these are our learning objectives, right? Now let us understand this further. Let us see what can we understand from this. Now, what are these unique properties that we are mentioning here? So a lot of the terms are already given here, but let's start with polarization. This is a very important topic, polarization, right? Very important. So if I go by the polarization, you will understand that the dictionary meaning of polarization is a separation. So what are we separating? Even before you understand this term in the scientific context, let us understand this in the political context where it is used much more. You often have heard about the various political parties polarizing the communities, right? So what are they doing? They're separating the communities, right? So here also, when I take this term and put it in the science, We are polarizing, separating something. So what are we polarizing? So we are polarizing, separating the charges. And we are already aware that there are two kinds of charges, positive and negative. So we are trying to separate them, right? This is the entire concept around polarization. So there is separation of charges. But the point is, how do these charges get separated? I mean, how? Okay, let me just rub this little bit here. Okay. So what we are trying to understand is how does this separation go about? How? How is it? How are they separating after all? So what we do is we apply some energy to it. We apply some energy so that our charges inside the material can get separated, and we call this applied energy as the voltage. So if you know what voltage is basically a kind of force that is used to push the electrons inside the conductor. Right. So voltage and electric field are also somewhat synonymously used, but here we will also understand the difference between the two, because electric field is this term which is used often in this topic. So let us understand polarization again, coming back to our topic. So far we have understood that polarization means separation of charges. What kind of charges? Positive and negative. But the question is, how are they separated? So in order to separate them, we need some kind of voltage, which is energy. Now this energy may not necessarily be the voltage. It can also be some other kind of energy, like let's say the heat energy, thermal energy, right? But in order to regulate the process, we apply our manual voltage, and heat energy is already there in the environment, and it creates polarized effect in the material. We will understand that how. Just give me a minute. So let us take this again here. Let us talk about the heat first. Okay, let us talk about the heat. So what happened if I provide the heat to a material, let's say not just the dielectric, let us say the material, some kind of material. Heat is provided to some material. So you will find that this process already give rise to polarized molecules inside the material. Why I am taking the term molecules? We are studying this process at the molecular level. Now you know molecule is made up of more than one element, like two elements, three elements. So these three elements, four elements could be of a different nature by charge, positive or negative. So they are probably consisting of positive charge, negative charge. Now there is a polarization of that positive and negative charge that we're talking about here. But the point to note over here is that they are random in nature. What do I mean when I say there is random polarization inside? Is that we are talking about the direction. Okay, we are talking about the direction, and that is why we call these polarized charges and molecules as random. For example, if I take something like this is my conductor over here. Inside this, I have got some polarized molecules, polarized charges. So this is my random direction of this. This is how they are getting polarized. All of them are random, right? No particular direction aimed at anything. Now this is random polarization. Now if I pick up just one small polarization from here, how does this look like? So that you can have a visual understanding of this process. I have got two kinds of charges. Let's say this is the positive charge and this is the negative charge. Now they are separated by a distance d. Now this entire thing is polarization. So far you have understood the process of polarization. Concentration of positive and negative charges on both the sides, and they're separated by a distance. Now the next question that arises over here is that how do we know how much distance and how far away these charges will concentrate, right? How would I know that? So again, we will understand that through our difference. How do I know how much distance is this? Now, if I talk about, because earlier we talked about why don't we call the, if you look at the upper portion, I have already talked about that why don't we call the dielectric as insulator. This was one of our learning objectives. So let's just focus on this learning objective here. So let's go back. And in order to classify dielectric and insulator, I will use the concept of polarization, right? So let us understand that now. When I have a insulator, what happens is that it does not conduct. It has no free charge carriers. That is why there is no conductivity. In insulator, you will often find that since there are no free charge carriers, there is no scope of movement of any kind of charges. There is no scope of movement, right? Movement of these free charges, which is possible in other cases in other materials. Charges, because they are not free naturally. Why? Because they are not free. That is why you will find that insulators do not undergo polarization. There is no polarization in case of insulators. However, we do have a small category of insulators with small, uh, which is smaller in nature, and we call them as dielectric, and they go through polarization. This is the main difference between the two of them. However, you will also find the relationship. We can also find out the relationship here. For example, the question that should come into your mind is that why do these things go through the polarization and not insulators go through the polarization? Because they have got very weak bonds which are holding the charges, but they have very strong covalent bonds which are not very easy to break that holds the charges. Covalent bonds are extremely strong bonds. That is why polarization is not easy, because to get the polarization you need to provide some energy. Maybe it is the applied external voltage, or maybe it is the heat or any other kind of energy. In this case, polarization becomes possible in dielectric because of the weak bonds, and therefore we make use of this. Now let us understand the polarization a little more here, so that I can give you why is polarization significant to us, and not just here but also in other materials where we use these dielectrics. Basically, whenever the charges are separating, let's say positive and negative, this is the positive charge and this is the negative charge, and this is separated by a distance. This is a polarized molecule. Now, what is happening over here is that this is storing electrical energy, right? So, you know by the law of conservation of energy that energy can neither be created and nor be destroyed. So, in order to store this electrical energy, we are applying energy into the material, and that energy is our applied voltage, which I have already mentioned. And this applied voltage is polarizing the material, and this material is storing that applied voltage in the form of electrical energy. And this electrical energy is stored in these tiny dipoles, and I call this as dipole. If you carefully notice the term dipole, let us understand what you understand by this. Di and pole. So there are two poles, di. Two poles, one is positive, another is negative. This is used to store electrical energy. And this is also the concept which is used in the capacitors. Capacitors are what? If you understand about capacitors, right? What are capacitors? They are basically used to store energy in the form of what? In the form of electric field. I have got two plates and there is energy stored here. How does this work? We will understand that later in detail in the next topic. But the point over here that you have to understand is polarization of any material is a very important way to store the energy, electrical energy specifically. Now, if I go back here, let us understand the polarization again, the dipole again. If I come back here, so what is happening here is there is plus charge, positive charge, and this is the negative charge. So what will happen is there will be electric field that gets created from positive to negative charge. Now this is the electric field. We'll discuss about this also, electric field. But right now you understand that when I have got two charges separated by a distance, there will be some electric field and there will be electrostatic flux. Now, how much electric field will be stored? So basically here we are talking about the strength of these electric field lines. Electric field lines. How much they will be stored is decided by the concept of dielectric constant. So we have given it a name so that we can understand about the properties of any material. If my one material has a high dielectric constant, that means it can store lot of electric flux, lot of electric field lines. So there will be greater electrical energy that can be stored in that material. But if the dielectric constant of that material, of some material maybe, let's say anything, is small, there will be less storage or maybe negligible storage of energy in that material. So in order to store the energy, we need to know the dielectric constant of any material. So this becomes an extremely important parameter over here, which we have named like this, right? So if I give you certain examples, for example here, just give me a minute. Certain materials which has got very high dielectric constant are your dry air, your vacuum is what? Nothing. And distilled water. So they all of them has very high dielectric constant. They have the ability to store electrical energy if polarized. Right. Now next, those which have very low dielectric constant are your plastic, rubber, and so on. They are pure insulators. They are insulators, right? And now you can understand that insulators has neither negligible dielectric constant, they cannot store energy, and they cannot even pass the flux lines well. Well, that is the difference between the insulator and dielectric. But in order to understand that small relationship, you can understand that. For example, if I talk about the relationship here, let's say I have to know about the relationship between insulator and dielectric. We can even represent that. It will be very easy to remember, right? So there is this big circle of insulator. This is the insulator, right? And within this bigger circle, we have some materials which are dielectric. So this is dielectric. So you can understand that not all insulators are dielectric, but dielectric is a part of insulator only. So this is how you can understand the relationship between the two. Now, next, our learning objective, if I go back to what I have defined it, let's see what our learning objective was here. So we have understood polarization. Why is it important? We have understood dielectric constant. We will also understand the electric dipole movement and dipole breakdown. But before that, I just want to give you a small detailed understanding of electric field, because this is going to come time and again in this topic and a lot more topics. Let us understand the electric field. Let us understand what does this electric field talk about. If I take another topic here, let's talk about the electric field. Sometimes we synonymously use this term with the voltage, but we are going to try to find out the difference between the two. So electric field basically tells you that there is a field. Where is this field? But where is this field? This is around some charge. I call it as Q. So any charge, positive or negative, there will be some field associated with it. For example, if I take this positive charge, there will be some field here around it in this space. Now, what is the significance of this field? Why are we mentioning this field here? Because this field has got some force. What it does is, electric field has some force through which it pushes, repels or attracts another charge. Now this again could be positive or negative. So this is how we define electric field. Electric field is nothing but a kind of force. If any charge comes in this field, let's say this is the field of positive charge and I put a positive charge here or put a negative charge over here, all these charges will experience some force. But in what direction? That we can find out, but that is not of concern right now. So this is what we understand by electric field. Now what we understand by voltage here is, voltage is also again a kind of force that pushes the electrons through the conductor. What it does is push an electron through the conductor. Through the conductor. So if I don't provide voltage, if V is equal to 0, what will happen? The conductor will not conduct. For example, in our appliance, in our home also, we know that we provide voltage to almost every electrical appliance and then only starts conducting. Because this electron requires energy, and where would that energy come from? That would come from this voltage. Voltage is what? It is the potential difference. Difference of what? What difference we are talking about? We are talking about the difference of charges here. What are these charges? These charges are like positive charge and negative charge. For example, let's say on one side I have got the positive charge, on another side I have got the negative charge. So there is a potential difference between the two. Now this potential difference is like energy. So how can I represent this energy? I can represent this energy in the form of electric field lines. Do you know now, do you see the relationship between electric field lines and the potential difference? Electric field lines are a way to store energy again. So here we are storing energy. And this energy is being provided to the electron so that it can conduct. So this is what potential difference is about, and this is what electric field is about. And then we associate electric field with the electric field lines also, depending upon where the force is being applied, depending on what kind of charge we have here and what kind of charge we have here. Let's say this as Q1 and let's call this as Q2. Depending on the nature of the Q1 and Q2, we can create electric field lines, and we can also decide the direction of the force and the lines. I will probably tell that in some other lecture. But the point over here right now is that this is what we want to associate ourselves with at this point. Okay. Now let us understand the electric dipole moment. Even though we have understand that little bit in the upper portion, but let us see what else can we extract out of that. So here we had talked about the tiny dipoles that gets formed and they store energy in the form of electric fields. Because you are not going to create some new energy, right? According to the law of conservation, it has to come from somewhere. It has to store. Electric field lines are a great way to store that energy. Now let us understand the dielectric breakdown. Now going by the dielectric breakdown. Now let us understand this topic. Let us start with the term itself. This is, we are talking about the dielectric breakdown here. So let us see, there is some dielectric substance that we are using here and there is some break happening. Some breakdown is happening. So what is this breakdown that we are talking about here is of important concern to us. So what is happening is we are talking about polarization into the material or in a dielectric material when we apply some kind of voltage. Right. So what happens here is that these applied voltage creates tiny dipoles. I can represent these dipoles like this. How are they getting created? If my applied voltage, let's say I put a voltage battery over here and this is the positive sign, this is the negative sign. So inside this dielectric material, the negative charges will be attracted by this positive charge. So what will happen? I will have here negative, 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 and negative, negative. But in this part, this negative charge will attract the positive charges. So I will have here positive, 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 positive. And if you look at it carefully, you will find that all of them are aligned in the same direction, unlike the random dipole moments. For example, if I show you above, let's go back here. Look at this. This is the random dipole moments inside the material, which is where we have not applied any voltage, is just because of some thermal heating effect. Let's say the temperature of Delhi increases, you will find such kind of behavior inside the material. Tiny, tiny dipoles being formed and they are placed in random directions because of the thermal energy. But here we are deliberately providing voltage so that we can align properly these tiny, tiny dipoles. But the question that you can ask over here are many. Why is this dipoles only this much bigger, not this much bigger? Why is this dipole not like this? One dipole created and it can be this big. Negative sign here, all positive charges over here. What does this distance of the dipole movement depends on? It depends naturally on the applied voltage, of course, and also on the nature of the material that we are not going into the detail. So let us come back to this and see what else can we understand from this. Here you will find that this dipole moment is basically nothing but the point of extent of this positive and negative charges. So if a substance has a greater dipole, electric dipole moment, it means that the distance, this d, is very high. If a substance has a lesser electric dipole moment, that means the d are very, very small. So you will find very tiny, tiny dipoles being formed. So naturally from here you can tell me which of them belongs to the insulator and which of them belongs to the conductor. Conductor have got the free flowing charges. So if I place a conductor instead of a dielectric, you will often find something like this. Let's say this is a conductor that I am placing instead of a dielectric and then apply some voltage. I will have very, very big dipoles being formed here. Let's say positive, all positive charges here and all negative charges here. And I have applied the opposite voltage this time. So this is my negative and this is my positive over here. So this is how the electric field lines will be formed here, positive to negative, and energy will be stored, and then the bigger, bigger dipole moments. But here in the case of dielectric, we have smaller, smaller ones. So the functioning of the dielectric is to store energy, and we will understand that in great detail in case of capacitor. This is also what is happening in case of capacitors for your kind information, right? Now let us come back to the dielectric breakdown. Now, in order to understand dielectric breakdown, we first understood what is happening at the molecular level with the dielectrics when we apply some external voltage. Now, if let's say I keep on increasing this voltage, so what will happen to these? When I'm increasing the voltage, that means I'm increasing the energy. I'm giving much, much more energy than what was being provided. And now when they are getting energy, they will be greatly formed. There'll be bigger, bigger dipole moments formed. This D will increase. And at a point of time, this dielectric material, which was not conducting up till now, start conducting. This will become a conductor where we have free charges, right? Why do we have free charge? Because we applied a lot of energy and they have freed themselves. Now they can freely flow through this material, and this material has converted into conductor. So the overall understanding of dielectric breakdown is that our dielectric material gets converted into the conductor. When does it get converted? When does it get converted into the conductor? When we apply a very, very high voltage. So this is the entire crux of the dielectric breakdown. There is something breaking. What is breaking? Dipole moments. Small tiny dipoles are breaking and free charges are getting released, and then dielectric gets converted into a conductor by its function. So far we have understood like all the learning objectives we have completed here. I hope this is clear up till here. So we are done with the difference, we are done with the polarization, we are done with the electric field, we are done with the electric constant, also dipole moment, and also dielectric breakdown. Let us also understand mathematically the mathematical expression of polarization over here that we have not covered so far. So we are going to understand the mathematical quantitatively what does this polarization do to the dielectrics and other materials. So we are going to talk about some mathematical expression, a small expression here. Before that, let me just come back to the diagram over here. Let us see this random behavior over here. So now I have already told you that in this case I have got some charge storage, energy storage in these tiny dipoles. But they are all randomly aligned. They are not in a perfect alignment. So basically, the one dipole moment will cancel out the other dipole moment and so on. So what will happen here is because of the non-alignment of these dipole moments, we will find that the net electric field over here will be equivalent to zero. And that is why there is no conduction. That is why there is no charge or electricity flowing. Only when we have got some voltage, then only some material will start conducting. But this is not happening over here. Now, if I go to the next case, this was my case number 1 here. Now, let us go back to our case here, which we have, where we have applied voltage. Let's see. So, this was the place where I had applied some voltage and I have got tiny aligned dipole moments. So what will happen here is that there will be some net electric field which is obviously not equivalent to zero because they are in perfect alignment, not cancelling out each other at all. Right. So there will be some voltage and there will be some energy storage and some slight conduction also. But why does not this dielectric still conduct? Because the applied voltage and the electric field that has got created inside, they are in opposite direction. For example, in this case the applied voltage is like this, but the electric field that has got created is this. So if I collectively add all of these dipole moments, the net field, and there will be some net magnitude of the electric field and some net direction, this net direction will come out to be opposite. So this will slightly cancel out each other, but not very highly. There will be some conduction. But if we want to cancel out both of them, we have to ensure that both of their magnitude are equal. So you can play with this in an experiment. Apply some voltage. There will be some electric field that will get formed inside. Then you can increase or decrease the applied voltage and then also see what is happening to the electric field inside and so on. Now, let's go back to the expression of the polarization here. What I want to do is I want you to understand the mathematical expression of polarization. Let us see that. So this mathematical expression comes out to be like this: epsilon naught and E. So you are looking at some new terms here. This is the permittivity of free space. And over here, this is a very important parameter which is called as a susceptibility. Susceptibility of what? Of dipole moments. So this is qualitatively, this term over here is telling you how much and how strong dipole moments are going to get created. If your polarization high is high, that means your susceptibility is high. So you have got a lot of dipole moments. If your polarization is low, that means the susceptibility is low because it's directly proportional, right? So this dipole moment, how many dipole moments, how strong dipole moments can get formed? This is defined by our susceptibility. How much a material is susceptible to making dipoles, right? Over here, this is the electric field that you apply, and this is the permittivity of free space, right? If I go to look at it here, this is the constant characteristic of the dielectric and is known as the electric susceptibility of the dielectric medium. Now, what does this susceptibility depend upon? This depends on the molecular properties of the substance, but we are not supposed to go in detail here. Now, let us understand this epsilon naught is the permittivity of free space. So basically, it decides that how much the electric field strength can be accommodated by the free space. How much before it actually breaks down? Because if you'll keep on applying the voltage, it will keep on forming the electric field. It will start conducting after a point of time. So this is the expression of polarization over here and depends on three things: epsilon naught, chi, and E. E is the electric field, and that is it for today.